Monday, there were some information direction. So for the quantum info people, I have this slide where I'm explaining the setting. So we're looking at electronic band structure. So this talk is just going to be about non-interacting systems. Of course, later on, if I talk about non-Hermitian Hamiltonians, as I said, these could describe interacting systems in some limit. But the kind of models I'll be solving are only going to be quadratic non-interacting Hamiltonians. And so there's a variety of materials that are actually pretty well described by this assumption. So in a Hermitian Hamiltonian, you have real energies. So for instance, for just a single electron in free space, you would have a simple dispersion relation. It goes like k squared over 2m, where k is crystal momentum. So I'm using the condensed matter convention of labeling momentum as k. And in a crystal, things get more complicated. Things get a bit more complicated than in free space because now your Hamiltonian is a matrix, right? And we've seen many examples of these matrices already. And these are tight binding models, and they have a certain number of bands. And so if you have a matrix H of k, you need to diagonalize it to get the band structure. So even though this is just my first preliminary slide, I'm going to ask if there's any questions just for this slide. And please don't be afraid of asking one.
What are the materials?
Oh yeah, good question. So I forgot. I took these photos in like this museum for crystallography. Very good. I should know this next time.
The one on the right is pi.
Thank you. Great. Okay. Okay, so let me introduce the different players in this. And before I get to non-Hermitian, I'm gonna remind you of the Hermitian story. So this is the bulk boundary correspondence, and I'm just going to show you one particularly famous example so that we are all on the same page, which already made appearances earlier in the conference, but without much introduction. So let me just fully introduce it. So I'm looking at a two-dimensional system. That's the simplest Hermitian topological phase that doesn't require any symmetries. So you might recall that topology is defined as the kind of equivalence relations of gapped ground states. So you can deform one ground state into another ground state without a gap closing or phase transition, and then these are said to be in the same topological phase. Now you could add another restriction in addition to the energy gap. You could require that symmetries be preserved along that deformation, and then you end up with a refined classification. But for this case, which is the Chern insulator, you actually don't need any symmetry. So you only need an energy gap in a two-dimensional band structure. So I'm putting the system in a real space geometry here on the left. So I have a two-dimensional bulk. When I diagonalize this Hamiltonian, I get some bulk states that have an energy gap, right? So I'm looking at an insulator. Some states below the Fermi level, some states above the Fermi level. And these, in my case, I labeled them using the momentum kx. Of course, since this is a 2D system, I have in fact two momenta. But I'm just not resolving ky. So this is why you have these fat blobs of bands that are all collapsed onto the same kx value. Just because I'm lazy and I don't want to do a 3D plot, and it won't be important later on. But do know that there's a ky.
You are assuming that the Fermi level is at the middle of the
right
of the gap. Is that an assumption of what you're going to say later?
No, it's not going to be important right now. So it's just because I'm a very abstract, I'm doing a very abstract theoretical argument, and so I don't care. So I just to make a nicer figure, really, but it doesn't matter. Yeah. It would only matter if there's a symmetry that somehow fixes zero as a special, for instance, particle hole symmetry in superconductors. No, but I'm not, as for now, no symmetries. Yeah. Later on, we'll have a symmetry. Okay. So we can define topological invariants for these bands. So I'm not going to give you the actual expression because it's a bit technical. You look at the eigenstates of these energy bands and you calculate an invariant out of these eigenstates. It's an integral over the whole Brillouin zone. And in the case of the Chern insulator, for instance, you have given you a model where you have one Chern number. So this is called the Chern number 1 for the lower energy states and Chern number -1 for the unoccupied conductance bands. And in general, this is a Z quantity. So Z meaning the integers. So it's a discrete quantity. You can't change discontinuously between, like as you do some adiabatic deformations that keep the gap open, it can't change abruptly. So it's a topological invariant that kind of tells you in which topological equivalence class you're situated. And it's an invariant we just calculate from the bulk states, right? So far, everything is bulk. So now I'm looking at a boundary, and I've kind of already, I kind of already knew that I'm going to look at this boundary that is situated along X because I've been using Kx as a good quantum number, and this boundary still preserves Kx, right? So this boundary is completely translational invariant only in X direction, so Kx remains preserved. Now we don't care about Ky anymore. That's why I didn't plot it beforehand. And the bulk boundary correspondence for the Chern insulator states that when you have a Chern number in the bulk, you have the same number of edge states on the boundary. It's a bit more technical because these edge states have an orientation, right? In this case, you see it going to the right. It might also go to the left. So the general statement is that the Chern number is equal to the right movers minus the left movers. So here we have two invariants that are both topologically stable, right? So the Chern number doesn't stay, can't change if you do something that preserves the bulk gap because it's an integer. Now the quantity on the right-hand side is an easy exercise to convince yourself that it also can't change. For instance, if you have let's say you have a chiral mode like this. So this is clearly a single right mover, no left mover. So what I could do, of course, is I could deform this like so, right? This is like just an adiabatic, I just pull this part downwards. But now you have two right movers, this one, and one left mover, right? So the full imbalance is still one. So you can't actually change this. What you could, like you could do another thing where you add like a crossing like this and then gap them out. But again, you have two right movers, one left mover. So both of these are topological invariants, and the bulk boundary correspondence states that they have to be equal. Okay, that's the Hermitian case. Are there any questions about this part?
You
Yes.
have two different C2D values on the slide. The one formula, what? How do you get two different values minus one?
Oh, right. So I should say that in the lower equation, it's only about the occupied states. So topology is defined only for the ground state in this case, which is filling all of the occupied bands. Yeah. Any more questions?
So did you just give an argument why you could look at the surface states and edge states first, and then say, because I cannot deform it without creating that movement, then I cannot do anything that influences the bulk. So it's kind of going the other way from the edge states to the bulk.
Right.
There must be a Chern number change if I do something to the system that would make the edge dispersion change in that way.
Right, like you can basically,
you
you look at the edge and you see that the edge has a kind of band structure that you can't, there's some invariant you can define for this band structure that you can't change adiabatically whatsoever, right? That must mean that the bulk has some topologically non-trivial phase. You can't relate it necessarily to the Chern number because that's just a different, right? You don't know, it must correspond to some invariant in the bulk. And of course, if you know a bit more about the Chern number, and if you know that it comes from, like, for instance, a magnetic field, and like you look at the cyclotron motion of the electrons, then you see that it's actually the same bulk invariant. But yeah, so from the edge alone, you just know that there needs to be a Z invariant because you can have Z of these and not change them, like any integer number is stable. Okay.
remember that he gave us a license to kill when he said that we have only prepared to talk for 10 minutes.
Yes. Very good. 10 slides. Okay, let's move on to non-Hermitian. So as I said, like these are the kind of, yes.
I have a question.
Please.
You say the number of states refers to some number of occupied bands, right?
Yes.
Then, so for bosons, this is clearly not working the same, right? And I don't know why.
But you're saying because there's no Pauli exclusion principle and there's no notion of.
For bosons, if I remember well, the number of states is given by the difference between the number of the two bands that are being joined.
Yes.
The two bulk states are being joined by the edge states.
Right. So in a more general case, you're right. It's the difference. It's just that in these simple lattice models, the occupied bands and the unoccupied bands must always add up to Chern number 0, because they form what we call a trivial atomic insulator. They, like, if both occupied and unoccupied bands are equivalent, topologically speaking, to the original lattice, which has Chern number 0, because it's just
But that's a
sites.
statement about a model rather than general statement, right? They can,
Right, but in general, okay, the general statement here is still true that if you in the bosonic case, it also holds. It's just you have to count all the Chern numbers that are below the gap.
okay.
And then it should hold, because in the end, that has to be exactly opposite of all the Chern numbers above that gap in any lattice model. So it's a statement about lattice models.
Okay, so maybe that is model the
Yeah.
sum of Chern numbers of all bands is C.
Yes.
That's it.
Right. So in a continuum model, you can avoid this, but in a lattice model, there's no way to avoid. Yeah.
Okay.
Okay. Yes.
What methods do you use to establish a bonding correspondence? And in a finite system, is there any caveats which look at?
So your first question is how do we establish that
Yeah.
correspondence?
I guess because we will also use something like this for the next.
Right. So in this case, the simplest way I know of is you take a model which has a Chern number in the bulk. So you just compute its Chern number in the bulk. And you do Dirac theory. So you kind of look at the low energy theory of that model. It corresponds to a gap Dirac cone in the bulk. And because like basically any topological insulator you get from a trivial insulator by some band inversions. In this case, you only need a single band inversion in the Brillouin zone. You do a Taylor expansion around that point that gives you a Dirac Hamiltonian. And you do a domain wall calculation where this Dirac mass changes sign across the boundary. And that gives you domain wall fermions that are these 0 energy states that cross the energy here, cross the Fermi level. And so you see there's a connection between the existence of domain wall states and the Chern number. And then by adiabaticity, if you have Chern number 2, of course, you must have Chern, two domain wall states and so on. And since we know that either of them are topologically invariant, you have the full correspondence.
Okay.
Because either of them can't change.
Why can you still use?
Sorry?
Like if you have the gap as state, why can you still use adiabatic arguments?
Well, no, you start with a gapped bulk. You derive the gapless edge state from the gapped Dirac theory in the bulk.
Okay.
So, but note that this adiabatic, like, so I shouldn't call it adiabatic, but this kind of invariance about the gapless states is not any statement about a gap, right? This is true for any dispersion in 1D. Any dispersion in 1D you can't change this offset right movers minus left movers. And normally this must be 0, but in the Chern insulator, the other part that kind of makes the 0 is located on the other edge, the boundary that's below that I didn't show you. So that's how the 2D system gets around this constraint. Yeah. Okay. Thank you for all the questions. So let's go on to non-Hermitian. So the kind of systems one might look at is open quantum systems with loss and gain, where you look at the coherent part of the time evolution is basically a non-Hermitian Hamiltonian, or interaction effects where the self-energy has a imaginary component, or classical systems. Like for instance, if you have electric circuits that are described by Kirchhoff's law, then if you add resistances into these circuits, that gives you basically a lifetime in a non-Hermitian contribution. So there's an important point here about how do we define topological phases in these systems. So in the case of a Hermitian system, we had a real energy. So all the energies were just along one line in the complex plane. Now in a non-Hermitian system, in general, we will have complex energies. So a real and an imaginary part of the energy. And there's two distinct cases. Here I'm showing you one case. It's kind of like the boring case. So what I've done is I kind of added non-Hermitian perturbations to this real spectrum on the left-hand side. And those kind of broadened these bands into these blobs on the right-hand side. But this kind of spectrum still has a gap that we call a line gap. So it's a gap where you can draw a line through the full complex energy plane and it never hits any states, any eigenstates. And in a sense, this is like essentially a Hermitian type of system, because without closing that gap, let me show you. Okay, so this is another case, which is the point gap, which I'll get to right now. But let's say with the line gap, so without closing that gap, you can collapse the spectrum again onto the real energy line and not close the line gap, right? So adiabatically, a line gap system is equivalent to a Hermitian gap system. You don't need to close the line gap. This is different for the case on the right-hand side here, which I call point gap, where you have states all around some region in complex energy space. And in that case, you can't collapse the spectrum. Right? Because if you did, you would end up with a gapless Hermitian system. And so you lose adiabaticity. Yes. Yeah. So good question. And I don't understand what it really means. So we don't want to do this. We look at the single particle physics, and we look at, for instance, either bosonic systems or classical systems that don't have this problem. But you're right, like there's some papers on interacting fermionic non-Hermitian, and they make some arbitrary choices, like only filling the real part, like up to the real parts. But I don't think this is well motivated. In the end, you need to have a particular physical system in mind, and then you come up from that system with the right rules for filling.
Just one simple question. Is there some sense in which the part of this diagram, or the imaginary part of the energy is zero, is some kind of limit where everything is again?
Exactly. So I'm basically showing you this limit in the red plots here. So I'm basically assuming, let's take a system that's line gapped. So the middle plot, and let's just set all the non-hermiticity to zero. All the non-Hermitian terms in the Hamiltonian I'll set to zero. Then in this kind of system, without closing the line gap, I get a perfectly Hermitian topology, like a Hermitian insulator, right? So that means that adiabatically speaking, this kind of non-Hermitian phase is the same as a Hermitian phase.
But would that physically correspond to a physical limit where that happens? So for instance, if you have a non-Hermitian
yeah,
that describes some out of equilibrium situation or some trivial system, is it true that in the limit where maybe the driving is very slow and eventually becomes, and maybe the coupling to the environment gets smaller and it becomes situation, then the spectrum for that limiting Hamiltonian would actually be the imaginary part equals zero of this diagram, or would it have changed?
It might change also on the way, right? It's not like the spectrum is not just the sum of the Hermitian and non-Hermitian. Like it might change, of course, a bit. But if you don't close the line gap,
you get this donut, for example, making up as we go along this route.
yes. It could still, you could have also you could close the line gap. So this statement is just as long as you keep the line gap open, this is equivalent to a Hermitian system. Yes.
Yeah. So when you couple a system to a path, it acquires a self-energy.
Yeah.
And then the lifetime is given by the imaginary part of the self-energy. Now what's the question is the following. It makes sense to have either a positive or a negative sign, because I don't remember the convention, but one of them would be a finite positive lifetime.
Yeah.
The other sign would be a negative lifetime, which is kind of scary.
Right.
So is there?
So in this particular system, it doesn't make much sense. You couldn't get that kind of term in this physical realization, but there's other physical realizations where you can get both signs. But when you have gain and loss, like in a laser, you pump some energy into the system, and that would give you the other sign.
Right.
Yeah. So it depends on the realization.
Okay.
Yeah. Yes.
Let me take advantage of the discursive nature of this session.
Please do.
To ask something that's always puzzled. This interaction effects thing, I mean, it is certainly true that if I calculate the Green's function for a particle in an interacting system, it has an imaginary part to itself.
Yeah.
But it's also true that that doesn't describe all of the physics that's taking place in the system. So there are features in two particle correlators that aren't represented in that self-energy, which might have to do with conservation laws, for example, conservation of charge.
Right.
So in what sense, I mean, I'd be tempted to say that in that case, I just don't have Hamiltonian dynamics for the part of the system that I've chosen to study. in what sense is it legitimate to say that I do have Hamiltonian dynamics, but the Hamiltonian is not Hermitian?
When you look at the short time dynamics of just the quasi-particles, so you restrict to that certain degree of freedom, which is of course not a well-defined eigenstate, so that it decays eventually. But at short times, their dynamics looks as if it's non-Hermitian. Of course, at long times, the system in the end is not non-Hermitian. So somehow it must be compensated. Somehow this energy goes somewhere else in the system, right?
Okay,
You're just not looking at that part.
But you say that in a Landau Fermi liquid, for example, that's done by the collective modes.
Yeah.
So if I just ask what's happening with quasi-particles.
Yeah. It's the same as like in an open quantum system where you forget the environment. And that effectively gives you a non-Hermitian evolution for the open quantum system. Yeah.
Thank you.
Yes, please.
What is how do you define the block state?
So in here, as I said, I'm only looking at single particle band structure. So I don't want to get into like it's a bit subtle of how to define a ground state in an interacting system like this. Because it depends whether you have fermions, bosons, and as like before we had this issue of the filling, right? And like the question is, how do you fill up energy, single particle energy states? And that will depend on the realization, on the physical realization you have in mind. So I'm only looking at the spectra here. All of this is just like the topology of energy spectra, single particle spectra. I'm looking at, yeah, eigenvectors is fine, but single particle eigenvectors. Yeah.
And you still need to define the ground state projectors.
No, that's just, it's equivalent. So in the Hermitian case, you can translate between the two. Right, and of course you can come up with a many-body statement for all of the single particle statements, but you can also look at only single particle, right? So you can define a Berry phase just in terms of the single particle projectors, or the Chern number just in terms of the Berry curvature, which is a single particle quantity. Yeah, and it's actually so you might think, oh, that's not relevant then for actual quantum system. That may be actually a valid comment, even though there are some realizations of these kind of systems in quantum systems in that self-energy sense. But there's many more, it's true that there's many more realizations in classical physics, which are basically single particle. Yeah. Yes, please. Yes, right. And we'll get to that, actually, it's going to be important. Yes, Aline.
Define your time scale of short time?
So the lifetimes here, which are the imaginary energy parts. Yeah, in the imaginary direction. Yeah. Okay. So all I wanted to get across in this slide is there's two kinds of gaps you can define for non-Hermitian spectra: line gap and point gap. And line gap is basically a Hermitian type of gap. So I'm going to call line gap topology Hermitian topology. Take any Hermitian topological insulator, add some tiny non-Hermitian terms, you get out a line gap phase. Point gap is more interesting because it's intrinsically non-Hermitian. You can't have any Hermitian system that realizes this, and you can't adiabatically connect to any Hermitian system. So you can have generally new phases that are enabled by the point gap. But it's also harder to realize. So my talk will be about how to get point gap phases out of line gap phases. And this is the Hermitian non-Hermitian correspondence. Okay, so let me show you the very simplest system for non-Hermitian topology. So as I said before, for the Chern insulator, it's a system that doesn't require any symmetries, just the energy gap. But it's also a two-dimensional system. And it's in fact the simplest Hermitian topological insulator that doesn't require any symmetries, right? It's a 2D system. In the non-Hermitian case, you can already have a 1D system that's non-trivial without any symmetries. So the classification of non-Hermitian and Hermitian topological phases is distinct. There's a new kind of 10-fold way classification. Now it's the 38-fold way because there's a lot more symmetries. And the simplest case is this phase, which is called the Hatano-Nelson chain. So in the simplest case, I'm just putting a hopping in one direction. That's it. So instead of hopping going both ways, you have hopping going one way. Unit cell is a single site. Nothing else. That's the system. There you go. So what happens with periodic boundary conditions? So I'm putting one hopping all the way back at the end of this chain. This plot here is the density as a function of position. So I'm just taking all my energy eigenstates, and since I can't really make sense of filling anymore, I'm just taking all of my energy states. Occupied, unoccupied doesn't make sense. I just take the full spectrum, and I plot the density that's obtained after summing these states, and I get out a, well, it's a completely homogeneous chain. I have translation symmetry, so I must get out something that's perfectly periodic, right? So I get one everywhere. Now, what happens for open boundary conditions? It's not a test. But I just wanted all of you to maybe think about what you think happens. And now you see what happens. So everything, well, you don't have this hopping that connects back, right? So everything ends up at one end. So the whole density must pile up. So I'm showing you an extremely trivial model, right? It's clear why this happens. But when you think a bit longer about this, it's extremely surprising. Yes.
Sorry, how do you compute this? I mean, you just solve the non-Hermitian matrix.
Exactly. So you have the matrix, and the matrix now is just looks like this, right? So you have a hopping 0, 0, 0, 1, and then you don't have the periodic boundary condition, and you diagonalize that matrix.
Okay.
And then you take the eigenstates, calculate psi squared for the density, and plot it as a function of. So that's what you get. That's what you get after. Well, in this case, it's
summing all the eigenstates
yes.
at a given size.
All the eigenstates at exactly. I'm calculating some. If my eigenstates are labeled by alpha, I'm calculating psi alpha absolute value squared at R, or in this case, I may call it. I call it R. Yeah. And this is my density rho of R.
So so let me just sum them all. I mean, so the plot there means that they are 0 everywhere except in the.
Exactly.
Okay.
But it makes sense, right? Because you're looking at eigenstates, and if you have any state away from the right end, it's transported to the right end. Right? In this system, you have no hopping to the left at all. Everything goes to the right. So the only stable state by the definition, an eigenstate stays invariant when you act on it with the Hamiltonian. It can be the right end state.
So all the eigenvectors of this matrix are the same?
Yes, so it's highly degenerate. Sorry, defective even. It's highly defective. This matrix is not like a normal matrix anymore that has an orthonormal frame of eigenvectors. Yeah.
Okay.
So it's crazy, right? Like we understand clearly why this happens because you only have one hopping, right? But when you think about it, it's a completely crazy thing because what we've done is we've only changed the boundary condition, right? Normally in a tight binding model, when you change boundary conditions, sorry, there was a question. Yes.
The calculation of the density profile, why do you just only the right eigenstate?
Only the right eigenstates, yes.
Why not the left and right?
That it depends on the kind of physical quantity you want to look at. But normally, the standard physical quantities are just defined in terms of eigenstates or right eigenstates. But it really, I think in this case, since I don't have a particular physical realization in mind, it's just an arbitrary choice. I want to tell you something that you can relate to the Hermitian limit where you have only right eigenstates. So what you're referring to, just to remind everyone, is that the Hamiltonian for a non-Hermitian system has right eigenstates, but it also has left eigenstates. So this is maybe call it psi tilde. Right, and these do not need to agree. In a Hermitian case, they always agree. Yes. Well, for what do you mean by finite? Like for an infinite system, I don't have edges, or do you mean like a single edge and an?
No edges.
Yeah. For an infinite system, is like in the periodic case, unless you do one edge, and then infinite in the other direction, semi-infinite, then you have the same thing actually. Yeah. Yes, please.
And what are the eigenvalues of this?
Coming up, next slide. Yes. Coming up. Okay, so what's crazy here is we've done a boundary condition change, which is an order epsilon change compared to a thermodynamically large system, right? So normally spectra don't change like that. Like there's a theorem even that like for an operator, like the continuum part of the spectrum can't change under compact perturbations. That's a statement for Hermitian linear operators. So it's kind of crazy that you can do an order epsilon change and you get an order 1 result here. But it's just a like peculiarity of these non-Hermitian matrices for which like a lot of intuition we have goes out of the window. Yes. So for a topological Hermitian phase, the bulk states all stay the same if you do open boundary conditions. You just get order 1 additional boundary states. Here you get order L boundary states, so extensively many. Yeah, very good question. Yes, please.
What happens when this boundary condition is very weak, walking from the last course? Very small.
Then you get back the, yeah, then you don't have this effect. So you really need to cut it. Yeah.
It's very tempting to think about this in terms of, and of course it's wrong because that Hamiltonian would be Hermitian. Just you have a particle on a line, you tilt the line, and you have a stop at the end.
Yeah.
Then the particles accumulate at the bottom. But of course, in a Hermitian Hamiltonian, there's always a hope in terms to go back. So Heisenberg makes it be a pattern at the bottom. But here is a point at the bottom. So it breaks Heisenberg's uncertainty principle. Clearly doesn't apply, right?
Right. So I guess that's also the reason that I'm thinking more about classical physics realizations here. Like in quantum, for instance, even Pauli exclusion would just immediately kill that state, right? And you will have spread out here. So you will have only an imbalance between the left and right hand part of the system in a fermionic system. But yeah, in a single particle, if you just look at the matrix, this is how the eigenstates behave. Yeah. Okay. Any more questions? So let's go on. So this is what is called the non-Hermitian skin effect, because you have all the eigenstates going to one boundary. So let's analyze this a bit more detailed. So now I'm adding another hopping. So I'm making things a bit more interesting. We have a hopping that goes back. Of course, if this hopping had the same strength, then I would be back in the Hermitian limit, and I would have a cosine dispersion, and everything would be homogeneous. Now, interestingly, as long as the hopping is different, like let's say this t prime is smaller than our original t, I still get a skin effect. So it's a bit of a stronger statement. It doesn't just hold in this very simple model we looked at, where we can immediately understand why there is a skin effect, but it holds in general. And in fact, it's a kind of topological statement. So I'll get to that. But for now, let's look at the details. So we have this Hamiltonian. I have t. Actually, I think I messed it up. T goes to the right and t prime should go to the left. But in any case, when you go to momentum space, well, the hopping to the right becomes e to the ik, hopping to the left becomes e to the minus ik, right? So what kind of shape does that make in the complex energy plane? You have like e to the ik is a circle, right? E to minus ik is also a circle, but with a different prefactor, so you get an ellipse, right? But you can add other terms. In general, you get some circular shape. That doesn't matter. So I'm just plotting this here in case like you have some slightly different system, but as long as you keep open this point gap, these are all topologically equivalent in the point gap sense, in the non-Hermitian sense. So I don't want to really specify the shape too much. So it's like, take some circular shape. And now here I fixed one reference energy, E0, for which I define the point gap, but it's completely arbitrary. I can take any E0 inside that circle. So this is the spectrum with closed boundary conditions. This is going back to your question. This is what it looks like in the complex plane, and I'm not resolving momentum. So you have to imagine that as we tune momentum from 0 to 2 pi, we go around that circle. Now let's do a technical trick. So I'm going to show you how to solve this, how to derive the skin effect in that like technical picture. It's like we define this Hamiltonian, which is called the extended Hermitian Hamiltonian. So this is just a technical thing, h bar, which is given by 0, h dagger 0. up to the energy E0 that we have shifted by some constant. So this by definition is a Hermitian Hamiltonian. And we can always write down this matrix, right? It's just a definition. Given any non-Hermitian H, I write down this matrix. And since it's Hermitian, we can apply a lot of the tools we know, and like we're much more familiar. This has a real spectrum, and actually it will have a gap. And the statement of H having a point gap is equivalent to H bar having a real gap. So this is just a normal topological or non-topological insulator. And in fact, for the Harton-Nelson chain, this is just a Su-Schrieffer-Heger model. So, right, like if you take the Su-Schrieffer-Heger model, it looks like this in momentum space. That's the dimerized limit. In the non-dimerized limit, I have a T prime somewhere. But in the matrix is really the same. It's like in the same topological equivalence class. So the Su-Schrieffer-Heger model has 0 energy end states due to chiral symmetry. These are pinned to 0 energy. And note that chiral symmetry in this Hamiltonian is guaranteed. I always can define my operator sigma as 1, 0, 0, -1 in this block matrix form. That matrix always anti-commutes with this Hamiltonian. So I always have a 0 energy, like if I can protect 0 energy end states. So it's a bit more stable, right? Because it comes out only from the definition of the Hamiltonian. In a physical system, chiral symmetry is only a approximate symmetry that relies on nearest neighbor hopping. In this case, it's part of the formalism. So take it for granted that any such non-Hermitian system, when you go to this Hermitian extended Hamiltonian, has a chiral symmetry. Yes.
So the SSH has 2 phases.
Yes.
One is topological.
Exactly.
Does this always go to the topological phase?
As long as you have, so this is a very good question. So as long as you have an imbalance between the 2 hoppings, it always goes to the topological phase. Yeah.
But doesn't it depend on the E0? That if the E0 is within like the
yes, you're right. Like so, if the E0 is outside of this point gap, outside of the circle, that's exactly tuning you from the topological phase to the trivial phase in the SSH equivalent model. Yeah. Yes, please.
Is this trick only work for point gap system?
This is for point gap systems. You could also do it for line gap systems, but you usually don't want to do it for line gap systems because these are already deformable by just reducing the non-Hermitian terms to a Hermitian Hamiltonian. So there's a more direct connection to a Hermitian Hamiltonian for line gap systems that we can't do here. Yes.
Very related to my question, is there a signature in the spectrum of H that would tell you whether you had a point gap or a line gap in non-Hermitian?
Not that I knew of. You would have to calculate some invariant for the eigenstates. So the issue is that any line gap is by definition also a point gap. It's just that not all point gap systems also have a line gap. So what you would have to do is you view this H bar as a chiral Hermitian topological phase and calculate its topological invariant, which lies in one of the chiral Altland-Zirnbauer classes, like A3, for instance. And then if that invariant is non-zero, then the corresponding non-Hermitian Hamiltonian must be point gapped and not line gapped. But that's a bit of a technical thing. Yeah. Yes, please.
H bar is the Hermitian Hamiltonian. You can do the feeling that you do the constructor, and then how can you think that to the non-Hermitian?
Yeah, so I'm not sure what that means because I'm just introducing this, I'm just defining this, right? There's no physical meaning behind H bar. I'm just using it as a calculational tool. Yeah. Yes, please.
How do I use the target space of this as distinction with the target space of the non-Hermitian?
What do you mean by target space?
So I'm thinking the target band structure, target ground space. The whole of this is
Oh, right. So you're asking why the bands, like how do you relate the topological classifications of the SSH? So the way they are related is that you can show that there's a gap closing in H bar if and only if there's a point gap closing in H. So they are one-to-one related, actually. Yeah. It gets more complicated with symmetries because with symmetries, E0 might break some of the symmetries of H, and then you will have to make sure that, like, depending on where you are in the complex plane, you do this mapping. But without symmetries, it's really one-to-one.
You make the same links with magnetic transport.
Yes, like now on H bar, you're back to the usual toolbox. Yeah. Okay. So I get zero energy states in the SSH model that are at the ends of the physical H bar chain. Translating back, a zero energy state of H bar means that H must have a state at E0, right? If you look at this matrix, that means H has a right eigenstate. So whether it's right or left depends on the chirality. This is a technical thing I don't want to get into, but it has to have one eigenstate. So what you get in open boundary conditions is that actually for all E0s that are in the point gap, you must have an end state. Right? Because you can do this trick and define H bar for all E0s, and it's always a topological SSH model as long as you're inside the point gap. So this is the skin effect in a from a spectral point of view. You have infinitely many states. Like I'm assuming a semi-infinite boundary conditions system where you have one boundary and an infinite system in the other direction. So you actually have an infinite dimensional Hilbert space, so it doesn't contradict that you have many, like actually infinitely many states here, one for every energy inside the point gap. Okay, that may be a bit technical, so I'm going to ask if there's more questions. Yes. Oh, there's also a question online.
The question: E0 itself has a tuning parameter for topological phase condition, but it's not in non-Hermitian autonomy. What does it mean?
Right. So the physical meaning is, I think in this case, there's actually no physical meaning per se. I'm just using this as a tool to show that all of the energies inside the point gap must have an end state. So I'm just saying, let's define this E0. For each E0, there's a different Hermitian H bar. And all of these H bars are in the topological phase of the SSH model. So all of the E0s must have an end state. So it's really like a technical tool. Yes. Yes, please.
I'm trying to think about whether I could draw this picture for a finite length chain. I might naively expect that the continuum of edge states would discretize
Yeah.
a grid or something. But I can't quite see what breaks about the argument that you have something at every node.
Right.
Is it that finite length SSH doesn't really have the edge states anyway?
Exactly, that they are it's that they are slightly split by exponentially small corrections. And so they are not exact zero energy states, and then you can't make a mapping between the Hermitian H bar and the non-Hermitian states. Right? They're like there's no one-to-one mapping of zero energy states anymore. Yeah. Very good. You solved your own question. Yeah. Aline, you had a question. Okay, great. Any more questions? Yes.
Can you generalize the technical trick? Can you put any n by n of diagonal matrix there?
Yes.
And play the same game?
Exactly. That's usually what's done. So any non-Hermitian Hamiltonian, you form this H bar. And then you analyze H bar as a Hermitian phase. Yeah.
And is that the basis of connecting the 10-fold wave with the
Exactly.
10-fold wave?
Yeah. So that's the main workhorse in the establishing the non-Hermitian topological classification. But it gets a bit more tricky because there's different non-Hermitian symmetries, more than there are in the Hermitian case. For instance, if you have spatial inversion symmetry in the Hermitian case, so if this was some H bar, for instance, then this inversion symmetry would just commute with the Hamiltonian if I is my inversion operator, right? But in a non-Hermitian system, so let's call this I bar because it's all Hermitian, sorry. In a non-Hermitian case, you actually have two options here, right? You can get back H, or you get back H dagger. And that also reduces to the same inversion symmetry in the Hermitian limit. And so that kind of complicates things, but this mapping with H bar is the main workhorse. So yeah.
We now have 30 minutes to the end of the students.
Yes. Since we have so many questions during the talk, should we just do like have a longer talk and no questions at the very end?
Yeah, if you want to have no questions at the very end, you have 30 minutes.
Oh, then I have to. Okay, great. Thanks for letting me know. Okay,
You've
great.
been very successful.
Yes, we're doing well. Like this is the third slide. Earlier. Right. Right, so exactly. So in A3, you don't have a two-dimensional system with a point gap. So that corresponds to A3. So you don't have a 2D non-Hermitian system class A, which would map to A3 in H bar that has a point gap topology. You only have line gap topology then. But in two dimensions, you have other classes like A2 dagger, which is time reversal symmetry plus the dagger here that has a skin effect, because that maps to some H bar with like two-dimensional permission classification. Yes.
When do you expect to be able to go in the opposite direction? So sort of start with the parasymmetric, like permission material, and then find something interesting. Is it sufficient for like the off-diagonal parts to be complex, or do you need something else?
It's sufficient for the off-diagonal part to have a non-trivial topological invariant.
Okay.
Yeah. Then, yeah. Okay. So let's go on. So non-Hermitian bulk boundary correspondence. So previously we did Hermitian bulk boundary correspondence with the Chern insulator. Now I'm doing non-Hermitian bulk boundary correspondence, and then at the end I'll do Hermitian, non-Hermitian bulk boundary correspondence. So just non-Hermitian for now. Look again. We look at it again at the Hartmann-Nelson chain. Now I'm setting T prime to 0, so this other hopping is 0 again for simplicity. So we just get a circle in the complex plane. And so I'm showing the bulk on the left-hand side as a 1D chain, and it corresponds to some bulk states that are along a circle in the complex plane. Now you can define a winding number invariant for this bulk, which is basically just calculating the winding around some reference energy E0 of the spectrum. So note that this is a spectral invariant. Normally in a Hermitian system, topological invariants are invariants of the eigenstates, not of the eigenvalues. In non-Hermitian systems, they are invariants of either only the eigenvalues, as in this case, or of a mixture of eigenvalues and eigenstates in higher dimensions. But in this one-dimensional case, it's really just a winding of all the eigenvalues. So plug in HK equal e to the IK, and you will find that this evaluates to 1 for any energy in the circle. Yes. Yeah, what it means is that it involves, so it's an invariant of H, right? And then H is an invariant of the Hamiltonian that you calculated using the full Hamiltonian. And the full Hamiltonian contains eigenstates and eigenvalues. So if you want to rewrite it in terms of the eigenstates and eigenvalues, you come up with an expression that actually contains both of them. Yes, and then you're good, right? Right. Because like in this case, we don't have anymore a notion of ground state or occupied states. The full spectrum is topological. It's not just that the occupied states are topological, but the full Hamiltonian is topological. All of these eigenstates give the skin effect. Yeah. Yeah, thank you.
Is it because the energy eigenvalues are imaginary and therefore the
Right. Yeah. Then you have a line gap. That's exactly the line gap phase. Yeah. Right. So splitting them into two clouds is what happens for Hermitian topological insulator when you add tiny non-Hermitian terms. Yes.
In case it's sure what kinds of eigenstates, like one which has this independent sound.
Yes, in general, you can have that. Yeah. So it depends on your Hamiltonian. In general, if you can just add on to this Hamiltonian kind of like by increasing the Hilbert space or line gap phase, and then you will have some states that don't participate in the skin effect. Yeah. Yes, please.
So if you only have right hopping, you have the state, right? Where you have a point gap. But imagine that you had like both way hopping and you gradually kind of one-way hopping.
Yeah.
Would you ever be in a situation where you go from a line gap to a point gap?
Right. As soon as you turn off the exactly opposite hop, like as soon as you introduce an imbalance,
Yeah.
you have your like this is your real spectrum along the real line, and it immediately opens as a tiny ellipse
I see.
that's just fed like order epsilon fed because you've done an order epsilon change. Yeah.
What if you have a gap? Then you bring this.
If you have a gap, then nothing's going to change unless you close the gap. So you end up with a line gap. Yeah. That's why it's so hard to get point gap phases. So you have to start with a critical permission system. Normally these are fine-tuned. But in this talk, I'm going to use edge states, which are critical and not fine-tuned. So we get around this problem. Yeah. Okay. So we define this bulk invariant. In general, that's some winding number. So you can wind arbitrary amounts of time. Of course, if this is negative, that just means that you wind in the opposite direction, right? So if you have a boundary, I explained before that all of these states inside the circle become eigenstates. And I can also define an invariant for those states. And I can relate the two. So the general statement is that this 1D winding number invariant is equal to the number of right eigenvalues at E0 minus the number of left eigenvalues at E0. So this goes back to this definition of right and left eigenvalues I made up here. And the skin effect means precisely that your matrix is defective and there's an imbalance between right and left eigenvalues. For instance, you could think, like, how can I break this? Let's just put a quantum dot at the end with a 0 mode, right? That state, you're putting something at the end that's like, looks like this, right? That will increase the number of right eigenvalues, but it will also increase the number of left eigenvalues at 0, right? Because clearly this Hamiltonian has both right and left eigenvalues 0. So it won't change this imbalance. Again, it's like in the chiral case where you can't change the imbalance between right and left movers. So this is a topological invariant on the end. And you can relate it to, like, as I've shown before, it's exactly equivalent to the binding number in the bulk. And this is what we call this non-Hermitian bulk boundary correspondence. So the skin effect is guaranteed. That's kind of cool because it's a completely general statement. No, like it doesn't matter what the actual Hamiltonian is. We only looked at very simple Hamiltonians before because I wanted to show you intuitively how the skin effect arises. But no matter what Hamiltonian you have, as long as it has a winding number, you will have a skin effect. So in a sense, the non-Hermitian skin effect is like the topological edge state of a non-Hermitian point gapped phase. And it's drastically different from a Hermitian edge state because it's order L edge states in this case rather than just order 1. Yes.
Can I see explicitly from the analysis you did a slide or two ago on the Hamiltonian chain that I'm not expecting to have the same number of right eigenvalues?
Yes.
For the left.
Right. If you want to see that explicitly, then look again at this H bar Hamiltonian. And I've only shown that this H bar should have a 0 mode. But we know we don't know if it belongs to the upper right or lower left corner, right? So that is determined by the chirality of the 0 mode. So I defined this chiral symmetry. And in the SSH model, these 0 modes at the end, they are eigenstates of the chiral symmetry operator. That's what pins them to 0, kind of, because if you have n of them, they are all eigenstates of the same chiral eigenvalue, so they can't gap out with each other. So the chirality determines whether you have a right or a left eigenstate. In this case, whether it's an eigenstate of H or H dagger. So a right eigenstate of H dagger is a left eigenstate of H. Yeah. 20 minutes. Okay, great. We're good. We're good. Yes, please. They don't have the same eigenvalue. They only have the same eigenvalue if you have a normal matrix, which is a bit more general than a Hermitian matrix. A normal matrix means that H should commute with H dagger. You can have non-Hermitian matrices that are not normal, And the skin effect is exactly like a measure of non-normality, where this condition fails. And that's why you have an offset, like this imbalance that I've showed on the next slide. Yeah. Okay. So finally, we get to the Hermitian, non-Hermitian correspondence. So, well, we start with Hermitian. So we start with the Chern insulator from before. But now I'm showing you both edges, because when we have a real system, we always have top and bottom edge, right? We can't make a semi-infinite slab geometry. So when I plot the spectrum in the Hermitian case, well, now I have a chiral mode that goes up as a right mover on the top edge, and then I have a left mover on the bottom edge, right? But since they are spatially separated, they can't gap out with each other. Now I view this as a non-Hermitian system, right? So that's just a perspective. I haven't changed anything yet. I just say, let's say this is a non-Hermitian Hamiltonian. Well, it has a purely real spectrum, so it's hard to plot, but I've kind of tried to indicate this using these lines here. There's like the bulk states that collapse onto lines, and then there's the boundary states that collapse onto each other. So not much has happened. It's just like I'm rewriting changing my perspective on the system. So now what I want to do is, I've looked at the non-Hermitian perspective, because now I want to add non-Hermitian perturbations and see what happens to this plot. So don't have momentum anymore. So we have to think about how these states will somehow project into the complex plane, where as you tune momentum from 0 to 2 pi along the edge. So what happens to the bulk states? Well, the bulk states, as a function of momentum, kx, there's still extensively many states as a function of ky, right? And remember that I've forgotten about ky. So actually there's blobs of bulk states that will emerge when I add non-Hermitian terms. I will get these clouds of bulk states. But the edge states, they are one-dimensional states. So they are, for any given kx, there's only a single state. So if I add a non-Hermitian term, and kx kind of changes already here, and in this case it connects along the real axis, that means that my edge states will remain one-dimensional lines that are somehow pushed into the complex plane, but they won't be clouds, they will be lines. So it will look something like this, for instance. This is just one case I'm showing you. And I'm kind of cheating a bit because I'm showing you the interesting case, but then later on I'm explaining how we can stabilize this case and like remove the non-interesting cases. So we have two blobs of bulk states with different Chern numbers that are connected by these edge states. So this is a well-known fact that has been described in lots of papers, and like at the beginning of this non-Hermitian band theory story, where people looked at something called a non-Hermitian Chern insulator, and you basically still have edge modes. You can still define a Chern number. Now it's a Chern number that you define in terms of left and right eigenvectors, but essentially it's a Hermitian kind of topology. It's a line gap topology. So like now the insight is, let's look at this for a bit, right? And see if we recognize anything. Yes. Yes. It has a point gap, right? Like because of the edge states, if you look at it as a slab, that's like a very fat 1D system. It has a point gap. So let's just like, this is just a technical thing again. So I'm kind of taking the view that all of this 2D system is just a very fat unit cell in the y direction, and like a 1D chain of these very fat unit cells. Then viewing this as a 1D system, it must have a winding number, right? Because of how the edge states connect in the complex plane. It's basically the same topology as the Hartrano-Nelson chain in 1D, but now it's a full 2D Chern insulator that as a full slab realizes this kind of topology.
Sorry.
Yes.
Isn't there a rather subtle dance going on here? Because we said previously that I would need to make the thing infinite you want in order for the edge state not to hybridize.
Right,
and
but
yet now you're thinking of this as a unit cell of a lower dimensional system, which seems to imply that it's fine.
So in this, you're confusing the directions, right? I'm taking a unit cell that's finite in y directions, but the system has a winding number as a function of kx.
But I'm saying if it's finite in the y direction, won't the edge states hybridize?
They won't, because in this case, well, okay, slightly, they will hybridize slightly, but these are not the skin effect end states, right? Remember, these are just the kind of Hermitian, like somewhat Hermitian edge states that are just pushed into the complex plane. There's no skin effect as of yet, as long as I don't open another boundary condition.
But as soon as they hybridize, I lose the point. It becomes a line gap.
Okay, so yeah, right. So in principle, you lose it slightly, but
I think Chris's point is that if you make that into a chain, you'll be squeezed it in this direction.
Yeah.
And the edge stays at the top and at the bottom, they have some thickness that they hybridize. So they are not separate.
Right. So the way I get around it here is I also give them different lifetimes to separate them in the complex plane. Right. So I could hybridize them if the orange mode would be on top of the red mode. But if they have opposite lifetimes, they can't hybridize in that sense. Right. But in general, you're right. Yeah. Yes, please.
Is the parallelity of the edge nodes somehow connected to the sign?
Exactly. Like
So is the edge matrix of the spectrum or can they be superposed or something? It's like they've got signs of the parts.
So the signs of the imaginary parts is not related to chirality. That's just an arbitrary choice I made. And I need to explain why I made that in the next slide. But the direction, the arrows are the chirality of the edge states. So it's still giving you a different sign if you change the chirality, because the arrows will go another way. So the arrows mean how the edge state disperses as a function of kx. So if I tune kx from 0 to 2 pi, I will, for instance, follow up the line like from down here to up here. Yeah, if it was a left mover, I would go down instead. Okay. Okay, so now we open boundary conditions in one more direction. So we open boundary conditions in the x direction. And now we get a skin effect, of course, because we have a winding number, right? But this skin effect has to show up at the corners because these are the only special points that we introduce, right? The Chern insulator per se doesn't really care about spatial degrees of freedom, so it doesn't know, so to say, on the edges that like the top edge should be different from the right edge. So it must occur at the corner in a general case. Yeah, so this is a correspondence between a Hermitian topological phase and a non-Hermitian point gap invariant. And actually it's completely general. So I should say that here I'm showing you the Chern insulator, and that Chern insulator case has actually been experimentally realized a bit later. After our paper came out in the gyromagnetic photonic crystal, so it's like a classical platform. And I should also point out Ashwin's paper, which has a complementary perspective. So this is a PRL 2019, where the authors showed that you can also start with a non-Hermitian point gap spectrum and look at the long time dynamics, where basically half of the spectrum has decayed. And that remaining half will be like the edge states of the anomalous edge state of a Hermitian topological phase. So it's a similar correspondence mathematically. Physically, it's a different perspective. So here we start with a Hermitian phase, like some material that has a topological invariant, and we add tiny perturbations to get point gap topology. Okay, any questions about this slide before we go on? Then actually, we made it to the last slide, I think.
10
so
minutes.
10 minutes. Okay, we will do it.
Well, I don't know.
Yeah. So I just wanted to be completely like show you the full thing, because what I've done previously in the last slide is kind of a sleight of hand, right? I've given you one particular way of introducing non-hermeticity, right? I've given you the most interesting way. Instead of this, we could also have this, right? And this would be much more boring because there's no winding number. There's no higher order skin effect. So you might say, oh, this is a question of the particular system. It's not so interesting, right? So we should make it somehow more general as a statement. So in this case, we need symmetries again. So this is the first time where symmetries show up. Without symmetries, there's no relation between the Hermitian topology and the non-Hermitian topology in the boundary. With symmetries, there is, and actually we only need the simplest symmetry that's compatible with non-Hermitian topology. So that simplest symmetry is inversion symmetry. But interestingly, it's this case where inversion goes to H dagger. And the reason is that, well, if inversion symmetry commuting past H would give you back H, you could actually show that the winding number must always be 0. And that makes sense because, well, we have a Hartmann-Nelson chain where everything goes to the right. That's clearly not inversion symmetric in the usual sense, right? So that symmetry is bad because actually all non-Hermitian invariants, all these point gap invariants are turning out to be trivial using that inversion symmetry constraint. So that's not compatible with any non-Hermitian topology. But this non-Hermitian kind of generalized inversion symmetry is. And actually, depending on the physical realization, that's like easier to realize. And in that kind of symmetry, you do have a winding number, it's still set classified, and all the other like higher dimensional non-Hermitian invariants are actually also fine. And it rules out this part, this case here on the right. Why? Well, these two chiral modes, they belong to different edges in real space. Inversion maps between the two different edges, but now it also daggers. Daggering means that it switches the imaginary part, right? So it means that the different edges must always have opposite imaginary parts. So this symmetry is actually enough to guarantee this correspondence, and then you can formally, a bit more formally, you can show actually that there's always a mod 2 correspondence. So the Chern number must be equal to this one-dimensional winding number defined from a non-Hermitian perspective, mod 2. Why not mod n? Why not as a z equation? Well, because clearly I can't say, given a Chern number, what the orientation of these chiral modes is. They could wind the opposite direction if I had just given them different imaginary lifetimes. So I can't tell. And you can also likewise show that if you add on, like if you have this is your 2D system, and you have like a skin effect here, or higher order skin effect at the quarters. And now you add a Hartmann-Nelson chain. Because of inversion symmetry, you have to add one on both ends. So you change the total winding number by 2. And that's why it's only defined mod 2. But and other than that, the correspondence is completely general. So it applies to any Hermitian topological insulator with a Chern number, and to any kind of non-Hermitian phase on the boundary with a winding number. It can't break unless you close the point gap. Okay, so actually this is my last slide, but since I have 5 more minutes, I'm gonna or maybe I should first ask if there's questions about this slide actually. Yes, please. Yeah, so that's not a one-to-one, because in the you can go many different ways starting from a critical point, right, to all kinds of gap systems. Yeah. Yes.
So you also have time reversal. So why you don't have the parity time only
Yes, you don't need, yeah, in this case I can't use time reversal for anything. So I haven't mentioned it. Yeah, but in principle you have it in this one model. But here you don't need it. The statement is still true if you break it.
I mean,
was that your question? Like whether you can use time reversal symmetry?
You don't need time reversal symmetry, you only need inversion.
I only need inversion symmetry, exactly. Yeah. Okay, yes.
So I'm sorry if I missed this, but you were saying you add like non-Hermitian perturbations. Is that just at the edge?
You can add them just at the edge, but you can also add them throughout the bulk. Since the bulk is line gapped, you don't change it much, right? You can't, if they are much smaller than the line gap, then you're fine. You can add whatever you want in the bulk. Yeah. Oh, yes.
It's like the inversion symmetry responds like as in the case of time reversal symmetry formation.
It's a bit different because you also map in real space. It's important that you map from edge the top edge to the bottom edge. Time reversal is local, so it maps top to top and bottom to bottom. So it's similar to time reversal for the spectrum, but for the eigenstates, it maps the top edge eigenstate to the bottom edge eigenstates. Inversion does.
All right, so it doesn't transform to the imaginary part.
It also transforms the imaginary part, so that is similar to time reversal.
Yeah.
But it also maps in real space. That's different.
All right.
Yeah. Okay. So I'm just going to flash this. I just want to show you that what I talked about was only this one special case of the Chern insulator. But you can do this for all the tenfold way Hermitian topological insulators. You add non-Hermitian terms and you check what kind of non-Hermitian point gap invariance you get out on the boundaries. And it's a bit more interesting than in a Chern insulator because now symmetries ramify into different non-Hermitian symmetries. For instance, for the P plus IP superconductor, right, you have two ways of realizing particle hole symmetry. You have the way where it commutes to H and where it commutes to H dagger. And actually only in one case you will get a non-trivial non-Hermitian invariant. Similarly, for the quantum spin Hall effect, you have again two ways of ramifying time reversal symmetry, but now you have two ways to get a non-trivial point gap invariant. And one of them will be mod 4. One of them is just as like Z2 invariant from the outset, so you don't need a mod. So to derive that is a bit of work, but what you do essentially is you look at the Dirac theory of the edge states and you add non-Hermitian terms to the Dirac theory and look at the non-Hermitian invariance of the resulting model. And then in 3D, you can do the same thing. And now you get something else. So in addition to a skin effect in like for the 2D phases, in 3D, you can actually get a higher order kind of chiral hinge mode. So it's not a skin effect. You don't have an extensive number of states. You just have order 1 states, but they cross the complex energy gap. And they are protected by point gap topology. So it's an altogether different beast. So it's still, even though it's like a kind of, it sounds like a Hermitian edge state, but you couldn't get it without this non-Hermitian point gap topology. The way to see that is that it's a hinge state that traverses along the imaginary axis, whereas normally in a higher order topological phase, hinge states traverse along the real energy axis. Right? Okay, and with that, let me conclude. And I have to thank my collaborators in Princeton. And I'm gonna ask if there's more questions, but for now, thank you a lot for your attention.
Thank you. Since I can now safely remind you, if you start 4 minutes late, we have 4 minutes for questions. Yes, yeah. That's already, no one lifted their hands anymore. I've seen 5 questions and that's one out of so.
Are these non-Hermitian edge states anomalous in the sense, or is there some current associated with it in the bar?
Yeah, so they are anomalous in the sense that you couldn't realize them in an edge lattice model. So in a similar way, like for a chiral edge state for Chern insulator, you can't realize a single chiral mode in a 1D lattice model. In the same way, you can't realize these non-Hermitian states in a non-Hermitian lattice model.
But yeah. There's some response functions in the bar that you can measure.
Yeah, so actually Schindler has a paper on the field theory for these and responses. And it's indeed some kind of current for the skin effect. But there's more interesting cases like that I showed later on that have responses like electromagnetic couplings and all of these as well. So for instance, you can have a response where you add a magnetic flux. So you pierce a magnetic flux through the system and you get a skin effect at the end of the flux. Yeah.
Okay, there were some other questions. Yes.
I would like to come back to the general question about the There, the treatment of industry has their particle cell energy, and because of causality, they retarded in advance. You have both in the picture of your edge state, you go both to the right edge, that's depending on the retarded or advanced. So my question is actually, so what are the implications of all of this non-Hermitian topology to materials where you have both copies that you can think about? Maybe you're thinking about tomorrow, think about positive and negative from far, this is part of
I must say I'm not sure because I haven't looked at that particular physical realization. I would have to write it out on a piece of paper and see. Yeah. But we're not just talking about the imaginary, like positive versus negative imaginary parts in my plots before, because those just coexisted, right? I plotted both in the same plot.
Look at the upper end of the equation type.
Yeah, exactly.
So, this was a realization of the like a imperial system. Then with a more that the
Yeah. Right, so one will have to write it down and see how to make this imbalance work in that system, and I'm not sure. So the physical like the experimental realization I mentioned briefly, that was in a classical system where you really can just put gain and loss at the two edges. Yeah. Yes. So there's a paper by Schindler about exactly that. So it's like field theory. If you Google field theory of non-Hermitian systems, you'll find it. Yeah.
Realization mentioned. What was concerned with the observation corroborates your investigation?
Yes. Good question. So what they observe is this higher order skin effect. So they look at a model that has a Chern number in the bulk, and they add tiny gain and loss, and look at it in this open geometry, and then they find that all the light modes, so it's a photonic crystal, so the light modes all end up in corners of the system. So they accumulate extensively.
Would expect that.
Yeah. No, yeah. Yeah. So right. So it's a bit more subtle because the correspondence, as I showed earlier, is in terms of the imbalance between right and left eigenstates of the non-Hermitian system. That's what's topological about it. And I think they didn't measure, like, I don't know how to measure that even. One like measuring that the Hamiltonian only has right eigenstates at that energy, but not left eigenstates. So you could build the same system with H dagger and then compare the two, I guess. But yeah, in the sense it's more compatible than exactly showing the relation. So it's more of a statement that the experiment is compatible with this. Yeah.
I'm afraid we ran out of time, so there will be a chance during the rest of the proceedings. And I apologize, and thanks again for.
Thank you.